Welcome to your own channel of Right Funda. Here is a question from electrodynamics. Let's go through the question first. A conducting coil held coaxially near one pole of a cylindrical permanent magnet as shown in the figure. If made to vibrate up and down simple harmonically with a frequency of 100 Hz and an amplitude of 1 millimeter, which is much smaller than the linear dimension of the magnet, the voltage induced in the coil has amplitude of 5 pi volt. Now, if the coil is held stationary at the mean position of the oscillations and a current of I is equal to 200 milliampere is made to flow through it, how much force will it experience? So what question is saying, if I say this is a magnet there, on this magnet uh, near the end there is another ring there, and you make it to oscillate like this ring is there, this ring is oscillated like this, and very small amplitude, of course, small amplitude, 1 millimeter amplitude is oscillated like this. If it is oscillates like this, then a maximum of 5 pi volt, this much V naught is equal to 5 pi volt is generated if it oscillates the frequency of 100 Hz. Now, I think that now it is kept fixed at this main position and a current is made to flow. Suppose a current is made to flow through this, then how much force it will experience if the current is 200 milliampere is flown in the wire in the same magnet, then how much force it will experience. Now you understood the question. Now pause the video and try solving the problem. After that you tried the solving problem, you again resume the video and you can see the solution. Now see what the question has been given and what we need to solve. You must have tried right now. So it is executing SHM in the y direction. Suppose I take this is my x-axis. Suppose this is my x-axis, and this I take as the y-axis. So other dimension will be z. That will be the xz plane. This ring is the xz plane here. Okay. So if this body is executing SHM, then I can write an equation. This equation, if I write move anytime in position to y distance is there, then y is equal to a sine omega t. That can be written. So if I write the equations for this, then I'll write the equation for this is equal to a sine omega t. Y is equal to a sine omega t. And if I differentiate, all of us know in case of SHM, if I differentiate this, then I'll get the velocity is equal to omega a cos omega t. There's the velocity that the y direction is equal to omega a cos omega t will be there. And this to this velocity as the SHM will be there, and due to the SHM, this body's velocity is in this direction there, and magnetic field will be there, and a moving coil or a moving rod inside a magnetic field, there is an EMF is induced in it. This is called the motional EMF. And we know that what is the value of motional EMF? We'll see the value of motional EMF is equal to dE in any small part of the wire is equal to B dot dl cross V. There is a cross product between dl and V. And this you see which direction the magnetic field, how this whole quantity will turn out to be. Let's see. So this quantity, this you'll see is perpendicular to velocity as well as dl. Okay. So this is perpendicular to velocity as well as dl, and this is B there. Unless otherwise this component of whole quantity along the direction of B will be figuring out here, and the perpendicular to B will be cancelled out due to dot product. So if you see right now in this case, the magnetic field, suppose this I say this may be at this side is a north pole, this may be a south pole, and magnetic lines of force will be going like this and this like this. Magnetic lines of force will go. Here also some field will be there. We don't know how the field is there. Suppose the field will be something like this. We don't know. Suppose whatever the field may be there, I can resolve the field here into two components. Suppose this is my field, the magnetic field is there. I resolve it two components. One will be along the rod. I solve the By component, and in the horizontal plane, on the plane of the ring, I call the Bx component. So this magnetic field I resolve into two components, and one component I call By, another component Bx. If you see out of these two components, which will contribute towards my magnetic field, I want to see. then you see that dl cross v, this quantity dl cross v is perpendicular to velocity as well as dl. So if you see, if this b ka the component, the b ka component which will be in the direction of v, in the direction of v, this by component in the direction of b. So by ka component, by component, and this is perpendicular to v, that dot product will be 0. So what will be contributing to a dy is the only the x component that will be responsible for the emf of the in the rod along the length of the rod. Along with the length of the rod, the emf that will be produced, that will be responsible or will be produced due to this magnetic field and thus motion. Which magnetic field? The x component magnetic field. For this there will not be any, this will be in the dot product, that will be cancelled out. By is like this, and b dot dl cross v will be like this, b perpendicular, that will be cancelling out. So only we need to take the by component. Whatever the magnetic field is there, only the by component or along the magnet component need to be taken. So we'll write this b is equal to, sorry, bx component has to be taken, and the component in the plane of the ring has to be taken. So in the plane of the ring, we have taken the direction at the x axis we have taken. So this is a bx component there along this axis. So this will not be figuring here, only this component will be producing the EMF. So we are at the bx into ds to t. So this is a small EMF, this is a small EMF induced the small length of the wire. So I can enlarge this figure. So this is my figure is oscillating like this. So if I want to calculate this one, I can integrate this b is equal to this maximum value. What is the maximum value? Maximum value will be there when the velocity is variable quantity. This body is executing SHM. As this is executing SHM, its maximum value, the velocity is a variable quantity. Maximum velocity, maximum speed is at the mean position. And at the mean position, we know the maximum value of Vy is equal to omega. So if I put the maximum value of V, I put Vy ka maximum value, I will substitute. Vy is that, is the moving in this direction. Maximum value I will substitute. I will get the B into omega nx, that is the maximum EMF that can be induced in the any small element here. So small dy is maximum value I calculate, that will be at the mean position. If this small EMF I will integrate, then I will get the total EMF on the ring. So this bx is constant quantity, this omega is constant quantity, amplitude amplitude is constant quantity. So I can write this E max is equal to b omega a, and over the two whole length I integrate this dl I'll integrate equal to 2 pi r out there. So I got the maximum EMF that can be induced is equal to bx omega a into 2 pi r. So if I see from this bx can be calculated, is that is equal to E max by omega a into 2 pi r in the denominator, and I put this one Vx is equal to omega is equal to 2 pi into frequency. Frequency is given to this, a the amplitude, and 2 pi r is the radius of this magnet that is given to us. So we calculated a formula for Bx. We calculated the formula for Bx is equal to this much. If I substitute the values, if you see, and if I substitute the value, frequency is given at the 100 hertz and the amplitude is given at the 1 millimeter. If this values I substitute there, and the radius the ring cylindrical magnet is not given to us, if I substitute the values, I can obtain an equation that in Emax equal to 4 pi and 2 pi into frequency equal to 100 hertz, and into 10 to the minus 3 is my amplitude, and 2 pi r, where r is the radius. I got the bx component, which is not known to me. I got bx component in terms of radius of the cylinder of cylindrical magnet. Now go to the second part of the question. What is saying that if the coil is held stationary at the mean position of the oscillations and a current of 200 milliampere is made to flow through it, how much force will experience? So there is a magnetic field there, and in that magnetic field the current carrying loop is placed. In a current carrying loop placed in a magnetic field experiences force, we know, and the force is given by this df is equal to I dl cross b. Now in this I dl cross b, we'll see again which component of magnetic field will contribute toward the force. Which component of magnetic field will contribute toward the force? So right now what happened? This is no longer SHM is there. Now SHM has been stopped, and what is happening? There is a current is flowing through this. This SHM is not there, and now a current is flowing through this. If a current is flowing through this and a magnetic field is there, there is some By is there and Bx is there, and let's see the due to which component of magnetic field there is a net force will be there, and this we can see again this component of magnetic field will contribute toward the force. For this component of magnetic field, you see ideal cross B, ideal cross B, ideal cross B, you see the DL and B, because it has to be ideal cross B you have to do. So by has to be perpendicular, so in the plane, and will be radially outward will be there or radially inward will be there depending on the current directions, and this will be cancelled out because of the force due to the By component will be cancelled out. And the Bx component they will add together either in the upward direction or downward direction. Right now you see the way it is given that in the horizontal component you see current will be flowing like this, current will be flowing like this, and magnetic field in the x direction is there at any particular point of time. So BdL cross Bx will be coming out to be the net force at this positions, and in this case if the magnetic field is like this moving like this, and it will be upward direction will be there. If the current direction is reverse, it will be in the downward direction. The way I have written the current, it will be in the upward direction, net force will be there. So if I put this one, so what is component important to me is the Bx, again the horizontal component is there, so ideal in cross B, and directions may be equal to upward or maybe downward depending upon the current direction, how the sense of current is there. So this net force can be calculated by integrating the small infinitesimal force, and again I is constant quantity, Bx is constant quantity. I integrate the dl, and integration dl over the whole ring will be equal to 2 pi r, I Bx into 2 pi r. So I is given to us, Bx I have calculated, and 2 pi r is a quantity there again. So if I take this value, this equations I obtain, this equation I'll write here, then this will be. So if I substitute the value I is equal to given 200 milliampere, and this your Px we have calculated this one, the box it is quantity there, and 2 pi r there. If I substitute the values, I obtain the force to be equal to, in place of I we have written to 200 milliampere, Bx is equal to 2 pi into 200 pi into 10 to the minus 3 into 2 pi r, this quantity you have written, and 2 pi you are written. If you write like this equation like this, here you see this 200 cancelled out, this pi cancelled out, 10 to the minus 3 cancelled out, 2 pi r gone, and what we left out is equal to 5 only. So the net force is equal to 5 Newton that we obtain.